So our project this year is to design an entry for the robotic mining competition. What that entails is basically making a robot that will be able to dig a lunar simulant for two 15-minute competition runs. Our team's making evolutionary improvements to the previous team's design, as well as completing their fabrication.
The team is awarded points for several design reports, outreach activities with K-12 students, and of course, how much regolith is mined. Points are lost based on the robot's weight as well as its overall power consumption. The purpose is to design and build a working robot. In our case, that starts with excavation.
Hi, my name is Mike Foster. I'm the excavation subsystem lead for our RMC project. The subsystem is responsible for digging the material and delivering the material. Our choice for excavation system is a bucket ladder. Essentially, it is a vertical conveyor belt with buckets attached that rotates into the ground so it can pick up material and drop it onto a delivery tray. So we have that two-part system. They're both attached to lead screws that can raise and lower the bucket ladder and delivery tray system simultaneously. So we're not dropping any of the material, and we can lift it up, bring the robot over to our collection bin, and drop off the material.
Hi, I'm Alex Perez. I'm the structure subsystem lead. Our primary focus is making a chassis stable enough to hold everything together, as well as one that fits within the size constraints given to us by the competition. We had a good foundation from the previous team, which allowed us to focus on the mass optimization of the chassis. To do this, we used Fusion 360's mass optimization software to identify which portions could be removed without destroying the structural integrity of the members.
Hello, my name is Kevin Landers. I am the electronic sub-team lead for this year's NASA robotic mining competition. We have our battery, which is wired to a digital multimeter. This allows us to display the voltage of our battery before connecting our switch, which is wired directly afterwards, to connect the circuit. We have everything wired through a power distribution board, which allows ample current and power to be drawn by each individual motor and motor controller so that we have sufficient power throughout our entire robot at all operations. Each motor controller has a fuse built into the power distribution board, which allows us to break the current in case there's any failure with the robot. We have pulse width modulation signals being sent to our motor controllers so software can easily integrate and tell them how fast or how slow to move.
My name is Steven Pazienza, and I'm the software sub-team lead. We are responsible for the navigation and excavation code of the robot so that it can complete its overall mission. By doing this, we use Python along with ROS, which is the robotic operating system, which allows us to control every output we need for the robot. As well as that, we need to incorporate software and hardware integration and testing. So with software code, we used a computer simulation called Gazebo, which allowed us to test our software code before hardware is even designed. And with hardware tests, we integrated our computer on board with electronics and allowed for all motor tests before completing the operation.